Okay, so we're going to provide some more background information here with the real and the complex numbers. We'll briefly go over that, and then maybe some matrices and binomial coefficients. Okay, so the real numbers, they're denoted by the same font. We use the Z for the integers by R. And I think of them as a number line. Here's a number line, here's 0, here's 1. Over here you have E. You might have a negative square root of 3 somewhere over here. All these numbers on the number line. So that's what the real numbers are the number line. And then what are the complex numbers? So if we look at the equation, x squared plus 1 equals 0 has no solutions in R. Because x squared is either positive or 0, so if you add 1 to it, it's going to be at least 1. So, but we can show, and actually, hopefully by the second end of the course of abstract algebra in field theory, you can actually show that there exists sets where any equation you can find a solution. So there are a solution to that exists. It's called I. So you can think of the defining property is I squared equals negative 1. Think of I as being the positive square root of 1. Sorry, the positive square root of negative 1. So then we define the complex numbers . And just like we use a bold-faced R for the real numbers, we use that same type of font for C, by C. And so what it is, it's all A plus BI, where A and B are real numbers. And I go through adding and subtracting them. Really what you want to do is you want to add, subtract, and multiply complex numbers the way you would with polynomials, treating the I as an indeterminate, but the only difference is I squared is negative 1. So how can we add numbers? So what we want to do is we use the regular properties, sort of treat like polynomials with I squared equals 1. And so one thing we might notice that R if we take a real number x we can write that real number x as equals x plus 0 times I, which is an element of C. So the real numbers are the real numbers is a subset of the complex number. And addition and subtraction is easy if you take two complex numbers. You would add the part without an I and add or subtract the part with an I. I should say in a complex number, A and C, that would be the real parts of the two complex numbers. B and D would be the imaginary part. So you can think of a complex number as represented as a real part plus an imaginary part. Multiplication is a little bit trickier. For the real part, you get an AC, and then looking through here, you can see that you'll also get a BD times I squared. I squared is -1, so it would be minus AC minus BD. And then BI times C, BCI, ADI, AD, so BC plus AD. What about division? Well, to get to division, we talk about a complex conjugate. So what is that? One thing we might notice, if we just take a number, A plus BI, and multiplied it by A minus BI, using our formula for multiplication, we would get A squared minus B times negative B is negative B squared, so A squared minus B squared, or A squared plus B. And then we get A times negative B, a negative AB plus B times A plus ABI. Or just this product, AB times ABI will give us that. And so, if Z is a complex number, with Z equals A plus BI for two real numbers, we define the complex conjugate of Z to be, we put a bar over it, so this is read Z bar, Z minus BI. So the complex conjugate is the real part of a number. The real part would be the same, the imaginary part switches some. We can actually come up with a graphical representation, a useful way of representing a complex number. So where do they live? So earlier we talked about the real numbers, they're a number line. What is a complex number? You can represent A plus bi as a point A comma B in the xy plane. So this is some number A plus bi, which is z. A, and that's B. So that would be how you would represent a complex number. And again, I hope there's an app. I put a link to it on the demonstration product on Wolfram there to kind of represent a complex number. So what would the conjugate look like? Z bar equals A minus bi, so it'd be the same thing, but now this would be minus B over here. So if you think of a complex number, the conjugate could be represented as, given any complex number represented as a point in the plane, the complex conjugate is attained by taking that point and reflecting it over the x-axis. This also allows us to do a little bit of division as follows. So it turns out, how can we divide two complex numbers? First of all, what is 0? If you have a complex number z, then that complex number is 0 if and only if, let me add something here. Let's give z, express it as a complex number A plus bi. So if z is a complex number with A plus bi, then we'll see how much of this board I record. Not quite all of it. So then z equals A plus bi if and only if both the real and imaginary parts equal 0. Okay, how do we divide complex numbers? I worked through that in some details in the note, so I'll just provide the answer here. So let z and w be complex numbers with w not equal to 0. And suppose z is A plus bi and w equals c plus di, then if you look at z divided by w, it turns out that's going to be c squared plus d squared in the denominator, and the real part we're going to have ac plus bd. That's the real part. And what's the imaginary part? It again has cb in the denominator, and the numerator would be bc minus ad. And so what that really is, if we go through and show the calculations, it turns out it's going to be z times z bar over the absolute value of w, where the absolute value of w is just going to be c squared plus d squared. That's maybe aside, given a complex number z with z equals a plus bi, then we define sometimes the absolute value of z, or sometimes it's just called the modulus of z. And by a calculation I did earlier, we note that if we take z times its conjugate, we in fact get the absolute value of z. So that's really one way of deriving that division problem, is just looking at that z divided by w and multiplying both numerator and denominator by the conjugate of w. So z times the conjugate of w, that's just z times the conjugate of w. W times its conjugate, we see, is always going to be what's called the modulus, or the absolute value of w. And I will put, if z happens to be a real number, then this is going to be, the modulus will just be the same as the absolute value. So if z is negative 2, you can think of z as being negative 2 plus 0i, so it would be negative 2 squared, give us negative 4. So that's actually the absolute value. And this is actually going to be squared here. The modulus of a number is just the square root. So what we've really shown is that the number times its conjugate actually gives you the square of the absolute value of that conjugate number. So then one way of thinking of z divided by w bar, it's going to be z divided by w, z times w bar, just divided by the absolute value of w squared. So let's look at another important way of establishing complex numbers. I should say establishing, but I guess a better term would be representing complex numbers. And again, that link I sent you for the Mathematica demonstration project, which does not require Mathematica. There's a free plugin that you can download is a nice way of switching between representing a number as a complex number in the a plus bi form and this other representation that we'll talk about right here. Okay, so let's start with this representation. Suppose we have a number z is a plus bi. Another way you can represent that is in polar form. And so that is we can think about it as given an angle theta and a length r. So z would be r times cosine theta plus I times sine theta. Or z would be r cosine theta plus I times r sine theta. So again, the connection is the real part is just r times cosine theta, and the imaginary part is just r times sine theta. So where r again is going to be the square root of a squared plus b squared, or just the absolute value. And theta is a solution to cosine theta equals r cosine theta equals a, and r sine of theta equals b. So that's a polar form. And so sometimes what we do is we write e to the I theta for cosine theta plus I sine theta. So one way to think about this, we can express a complex number. Well, we can certainly express it as a plus bi, the real and imaginary part, or we can express it as a polar number as r e to the I theta. Well, we know there are properties of exponents. And so what we need to do is we need to show this exponential notation is justified. Because if it's truly going to be an exponential function, what we need to claim is that if I took r1 e to the I theta 1 times r2 e to the I theta 2, that would give me r1 times r2. And then what do if you multiply exponents? You multiply x to the r times x to the s, you would add the exponents. That would just be x to the r times s. So we need to show that's justified by showing that property holds. So let me attempt to do that. So R1 e to the I theta 1 times R2 e to the I theta 2. And so we've just defined what this is. This is just R1 cosine theta 1 plus sine theta 1 times I times R2 cosine theta 2 plus sine theta 2 times I. So we can multiply these R1 and R2s together. We have R1 and R2. Let's see what happens here when we move this out. Then we FOIL cosine theta 1 times cosine theta 2. And then here we have a sine theta 1I times sine theta 2I. So that's sine theta 1 times sine theta 2 times sine times I squared. But I squared is just negative 1, so that becomes minus sine of theta 1 sine of theta 2. So that is the real part. What about the terms that involve I? How would that work? So I have a cosine theta 1 times I sine theta 2. And I have sine theta 1 cosine theta 1. So that would be plus sine theta 1 cosine theta 2. And then a plus sine theta, cosine theta 1 sine theta 2. And let me make sure I have this projected further, far enough. Maybe zoom it in a little bit for you. Well, what is this? So this is R1 theta 2. Cosine, cosine, minus sine, sine. That is exactly cosine of theta 1 plus theta 2. Then we have a plus sine, cosine, cosine, sine. That's sine of theta 1 plus theta 2. And that's times I. But this is exactly R1 times R2. This is exactly e to the I theta 1 plus theta 2. And we can generalize this into a Demoivre's theorem. Which basically says R cosine theta plus I sine theta to the n is just going to be r raised to the n times cosine n times theta plus I sine n times theta for n in z, n greater than or equal to 1. And this is sometimes indicated in the note called Blau theorem. So that concludes a review of some of the things about complex numbers. And we're going to use these pretty soon. We have a little bit more to cover in review, and then we're going to introduce some groups, and we'll be using this complex, and particularly these formulas for Blau theorem as a useful example to help generate some groups.